Last time we started section 4.2, we were looking at prime and composite numbers. We talked about the fact that prime numbers are numbers that have exactly two factors, themselves and the number 1, and that a composite number has more than two factors. We took a look specifically at finding prime factorization with factor trees and talked about sort of the benefits and the possible drawbacks of that one, and then also this division algorithm on the right-hand side, and again, the benefits and the possible drawbacks of that one. So the next example that we're going to take a look at has some numbers that already have some exponents with them. So I would strongly encourage you not to multiply these back out. That would be moving in the wrong direction, because your goal is for it to look something like what we have in these boxes down below, where it has prime factors to powers, and it's already in a form where we've gotten the pieces sort of broken down. And this one, while not prime factors yet, is closer to being broken down than it would be if you start multiplying things back out. Does everybody agree with that? Okay, so what we're going to do, instead of actually taking the whole number that we were given to begin with, a big, large, a large value, and then factoring it into its components, is we're going to factor each of the pieces that were given into its components. So for instance, if I take the number 16, and maybe I created a small factor tree. Maybe you don't even need a factor tree on this one to know. You got 4 and 4, and you got 2 and 2 and 2 and 2, and you got lots of 2's, right? 4 of them, in fact. What your goal is to take each of those individual smaller values, 16, 81, and 6, and to write it as a prime factorization in and of itself. So for instance, the 16 itself is 2 to the 4th, and then you'll notice this exponent right here, 4, would be on the outside of the 2 to the 4th.
Why is there another exponent on the outside?
Because it was there to start with.
Okay.
It's already there.
Oh, because we only did 16, we didn't do 16.
Right. We were ignoring the power that was on it before. We only looked at the base 16 and we broke it down. So we are basically replacing the 16 with its equivalent factored form, 2 to the 4th. And we can do the same thing with 81. So let's take the number 81. I'd like for you to factor it down in a factor tree or in a division algorithm, whichever one appeals to you most. If you do a division algorithm, it looks something like this. If you do a factor tree, it'll look much like the one that we started with. What is the factored form of the number 81?
3 to the 4th.
3 to the 4th. And just like the last one, it's got another exponent of 4 out here that I need to put back into the exponent on the number that was previously 81. Now 6 is much simpler than the 81 or the 16 was. What is 6? 2 times 3, right. And it has an exponent on it of 6. Now you'll notice all I have now are primes in the bases, right? I have 2's, I have 3's, I have lots of exponents to clean up, but the prime part's done. Does everybody see that okay? Okay. So what do I need to do? Well, now I need to use properties of exponents that we talked about in, I think it was like 3.4 or 3.5. So what do I do when I have an exponent and an exponent like this on the base 2?
Multiply the two numbers.
I do. I multiply them. So this is 2 to the 16th. And I'll do it the same way over here on the 3. It would be 3 to the 16th. Okay, so that's the same rule used twice. What do I do when I have a 2 times 3 to the 6th? Yeah, there is a distributive law of exponents that says I can write this as 2 to the 6th and then write it as 3 to the 6th, right? And then prime factorization notation means that I don't repeat the bases. And right now I've got 2 in there twice, I've got 3 in there twice, and I want to consolidate. So what will I do to combine 2 to the 16th and 2 to the 6th? Yes, you add the exponent. So what do you get when you add the 16 and the 6th? 22. And we'll do the same thing with the 3. What do you get when you take the 3 to the 16th and 3 to the 6th? 3 to the 22. Okay? So you're starting with something that's sort of partially broken down, and you're breaking it down further, combining terms that have the same base, adding exponents, and so forth at the end. Any questions on that one? Okay, we're going to take it a step further. This one looks like two numbers that are already in prime factored form, correct? Primes of 2s, 3s, and 7s, they've got exponents, but somehow we're adding them together. And I'm sorry, but you can't just directly add things like this together, right? And if you wanted to look at smaller values to think about it, if you think about if you had 2 squared times 5 squared plus 2 to the third times 5, again, you can't add 2's together and 5's together because they're multiplied by something else that are not alike. They're not completely like terms. So what you can do, however, is you can look for what they have in common. So if you'll notice, both of them have a 2 in it. So I'm going to write it down. Both of them have a 3 in them. So I'm going to write the 3 down. And both of them have a 7 in them, so I'm going to write the 7 down. But the question is actually how many 2's do they have in common? How many 3's do they have in common? And how many 7's do they have in common? So let's start with the 2's. How many 2's are in the first expression? And by first expression, I mean all of this.
2.
There are 2. How many 2's are in the second expression? 4. So how many 2's do they have in common? 2. They both have 2. So I'm going to start by writing down that they have 2 2's, or 2 squared, in common. How many 3's do they have in common? 4. There are 5 in the first one, 4 in the second one. That's 4 in common. How many 7's do they have in common?
55.
Yeah, like all of them, right? Yeah, 55 of them. Now what we did is we found out what they have in common, because what we're going to do with that is we're factoring it out in front. So what I'm going to do next is I'm going to put parentheses and I'm going to write down what they don't have in common, or what the leftovers are. So again, if I look at the first expression right here, how many 2's do I have left over? None. I took care of all of them, right? So I don't have to worry about the 2's. How many 3's do I have left over? There's 1 3, so I'm going to write a 3 in here. If you want to write 3 to the 1 to be very clear to yourself, that would be fine.
Why did we not have any 2's left over? Because you would get 2 to the second, not 2 to the fourth. So you would still have those.
Because I'm only looking at the first one, Hannah.
Oh, okay.
I haven't done the second one yet. I will,
Okay.
and I'll have that left, but not there yet.
Okay, sorry.
It's okay. Okay, so I had from the first one, the one that's underlined in blue, I had 1 3 left. Did I have any 7's? No, I took care of all of them. Now, what's next is an addition sign. Do you guys see that addition sign? Okay, I'm trying to change it to a different color. That's the one I wanted. The addition sign will have to be present down here. It doesn't just disappear. I need to add the pieces that are left over together. There's a 3 left over from the first piece. What's left over from the second piece? Okay, there's a 2 left over. In fact, there's 2 2's, a 2 squared left over. Any 3's? No. Any 7's? No. All right, so I still have a 2 squared. I have a 3 to the 4th. I have a 7 to the 55th. And the question is, what is 3 to the 1st plus 2 squared? It is 7.
So you actually added up?
We actually added up. 2 squared is 4, and 4 plus 3 is 7. But now I have a 7 to the 55th, and I have another 7, so what does that tell me?
7 to 56.
There's 7 to the 56. There's a 2 squared in the first piece, there's a 2 squared first, there's a 3 to the 4th second, and then there's a 7 to the 56. And it's all done by looking at things that are in common, and pulling them out, and then seeing what's remaining of the things that are not in common. All right. Fundamental theorem of algebra. Anytime people tell you something's a fundamental theorem, it means it's awfully important, right? Fundamental theorem of arithmetic is this one. Sorry, I didn't even say arithmetic. I said algebra for it. Arithmetic says, each composite number can be written as a product of primes in one and only one way, except for the order of prime numbers. So this is actually the reason why it doesn't matter if you use a factor tree and I use that division algorithm. We're going to get the same list of prime factors to the same number of exponents, and the only thing that could possibly be different from my order and your order is that we don't necessarily write them down in the smallest to largest, base of exponents or something like that, bases of our exponents. It's the only thing that could possibly be different. But we will have the same compilation of bases and exponents. It's a fundamental theorem of arithmetic. Theorem 414 says, this is what I actually thought you were asking me earlier, Hannah, when I was reading your question.
Yeah.
If D is a divisor of N, then n divided by d is a divisor of n. What this theorem actually tells you is that the divisors come in pairs. So let me give you an example of this one. For example, 4 divides 32. Do you agree? Yes. Yes. So what is 32 then divided by 4? It's 8. This theorem says then that that 8 will also divide 32. And everybody said, yeah, it does. And the gist is that these two numbers come in pairs. So if you find one divisor, you automatically find two divisors. Now, it's a little tricky. You know, it might be an unhelpful divisor, right? Like 6 divides 36. Okay, but 36 divided by 6 is 6, so I just get another 6, right? It doesn't have to be distinct. These pairs are actually identical, right? This pair is itself. But it comes in pairs. Divisors come in pairs. All right, this is a really helpful one. This one tells us that if n is a composite number and n does have a prime factor, then n has a prime factor such that p squared is less than or equal to n. Now, it's a little bit more helpful to look at it from this perspective. P is less than or equal to the square root of n. So look at Theorem 416. It says if n is a whole number greater than 1, and it's not divisible by any prime factor p such that p squared is less than or equal to n, or that p is less than or equal to square root of n, then n is prime. So let's say that somebody gave you a really weird number, 737. You're like, 737. I'm going to test some primes. I know it's not divisible by 2, right, because it's not even, so I don't have any even prime or any even divisors. But how far do I have to keep dividing to find out that this really is a prime number? That's a legit question, because you don't want to divide by every possible number smaller than 737, right? That would take a while. So the question is, when can I stop dividing and say, yep, it's prime? Well, the answer is you can stop dividing at the square root of 737. So somebody tell me from your calculator, what is the square root of 737? With one decimal, if it's got a decimal. 27.1?
Yeah.
Okay, 27.1, which means that the number 737, you only have to test the prime number smaller than 27. Oh my goodness, who would have thought you could have stopped that soon? That's important information, isn't it? That's time-saving information. That gives you less work to do, and that's really useful. So here's an example, 967. Again, it's a weird number, right? The question says, what is the greatest prime you must consider to test or consider testing to decide if the 967 is prime? So you take 967 and you find out what is its square root. 31 point what? 0.1? Okay. So 31.1. Obviously, this is not a prime number, it's a decimal, right? What's the smallest prime number, the biggest prime number smaller than 31.1? 29. Is 31 prime? Yeah, actually 31 would be the number. Okay. So the question is, what is the greatest prime you must consider? The answer is 31. You have to make sure that you're answering with a prime number. Okay, so if the answer here had said 32.1, you wouldn't answer 32, right? Because 32 is not prime. It still would be 31. So you want the biggest prime number smaller than the approximation with that square root. 31. You wouldn't have to test any higher than that, and you would know whether or not it actually divides. Show that if 1 were considered a prime number, then every number would have more than one prime factorization. All right. So give me an example of something that's composite. Any number. Don't make it too big because there's no need. Just a small number.
4.
4. Fabulous. That's very small. I like that one. Okay, so we have the number 4, and we know that 4 is 2 times 2, right, Hannah?
Mm-hmm.
Yeah. Definitely that's a prime factorization of the number 4. Agreed? The problem is that if 1 is a prime number, then 2 times 1 would also be a prime factorization. And if that weren't bad enough, so would 2 times 2 times 1 times 1. And so would 2 times 2 times 1 times 1 times 1. And this process could go on forever, right? You could always add some more 1s in there, not add, but multiply some more 1s in there, and it would be another prime factorization. So this is an example of showing that if 1 were considered a prime number, this is a very concrete example, right? The number 4. But we'd have infinitely many expressions of what 4 would look like in its prime factored form if 1 were a prime number. Can you kind of see why, practically speaking, we don't want 1 to be prime? Yeah, we don't want 1 to be prime. Okay, let's read through this one. We'll pause and we'll pick up next time. Mr. Arbor wants to plant apple trees in a rectangular array. Okay, so we're going to put them in an order in a rectangle. It says if he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. Can you guys picture what's going on?
Yeah.
This is like the muffin tin stuff, right? This is like your bottles of soda or cans of vegetables. You're going to put them in a rectangular array. Can you give me one example that would work if he has 36 saplings? 6 by 6. Right? Is that the only answer? No. And we will finish the rest of the answers next time.